Greetings, fellow mathematicians. We're going to go on a journey using complex numbers to solve an equation, sine of x equals 2, that has no real solutions. Now, let's first understand why this equation has no real numbers that are solutions. You might recall earlier from pre-calculus or through the calc sequence that sine of x as well as cosine of x is strictly between 1 and -1 for all real values of x. Graphically, you can see that here with the graph of sine. Your graph stays between y equals 1 and y equals -1, and the value 2, that's above the graph of sine. So there is no way you're going to have any real value of x for which sine of x will come out to equal 2. So right from the start, we can forget about this equation have any real solutions. Now, we might be thinking, going back to algebra, certain equations, if they don't have real solutions, they might have imaginary or complex solutions. And why we should be maybe thinking about that now is we now have access to Euler's formula, which is going to allow us to do a lot of interesting things with trig functions, complex exponentials, and hyperbolic trig functions. Now, there's two identities down here at the bottom, which we're going to use right now to get motivated and build our intuition. You can easily prove these. Go back to your identities for cosine and sine in terms of complex exponentials, and just replace in each of those x with ix. And the only thing you need to be aware of when you do that, you're going to get I squareds in those exponentials, and I squared, that comes out to -1. Rearrange it a little bit, and you'll get these identities. The sine identity, that takes a little bit more work due to the factor of I in the denominator, but you can prove that just by manipulating, get rid of your i's in the denominator, put them in the numerator, and you should get that for little effort. Now, again, we are forgetting about x in our equation being a real number, so let's try to at least take our trig functions, cosine and sine, and let's plug in imaginary numbers. Now, be careful here. Notice we have ix. That's already looking like an imaginary number. So in these identities, we're going to interpret x right now as being a real number. So a real number times I is an imaginary number. Now let's just pick a value for the real part here, x. Let's go with x as 2. So let's see if we can get an idea of what cosine of 2i might equal. Now again, these identities give us an idea. We're just going to be replacing here x with 2, and cosine of 2i, that comes out to hyperbolic cosine of 2. And if you go ahead and punch that into a calculator, you can use your identities here. If you're not familiar with hyperbolic trig functions, you can define them in terms of regular exponentials. And what you should find is this comes out to about 3.76. And why that is important for us in trying to solve this equation, sine of x equals 2, is notice we now have a value that is bigger than 1. Now, again, this is cosine of 2i. We're trying to eventually solve this equation, sine of x equals 2. But at least this gives us some hope to think if we use imaginary numbers and plug them into cosine and maybe sine, we can get a value that is bigger than 1. So that, I think, looks promising. Again, make sure you realize sine of x equals a number bigger than 1, like 2, has no real solutions. But for cosine, if we plug in imaginary numbers, we can get a value bigger than 1, like 3.76 here. Now again, this is cosine. Let's try to go ahead and plug in 2i to sine. So we're going to replace here x with 2. and we'll get sine of 2i. And having already gone through arriving at that identity down there, we're just going to plug that in. We're going to get I times hyperbolic sine of 2. And again, you can punch that in. You should find that you get hyperbolic sine of 2 is about 3.63. So we can say this is approximately 3.63, but times I. And again, the part multiplying I is bigger than 1, getting us into what we're looking for here, like sine of x equals 2. All right, now we can see here, if we take our sine function and plug in an imaginary number, we get an imaginary number as output. Regular sine of x, well, if we plug in real numbers, we're going to get real numbers between -1 and 1. So what we might be thinking, trying to combine these ideas, is, well, this part comes out to a real number bigger than 1. Your sine version, that comes out to a number for the part multiplying I also bigger than 1, but it's imaginary. Maybe we can try not looking for real or imaginary solutions, but let's try looking for complex solutions. So let's immediately change our equation here. From thinking of x as being a real number, let's interpret x as being a complex number. So our equation might look like sine of x equals 2. From before, we're just going to change the variable just to kind of not lose sight that we're thinking of x now as a complex number. You might be familiar or comfortable using that as now z, usually the standard variable for complex numbers. So we're going to rewrite this as sine of z equals 2. And we're going to think of z a complex number as having a real part x and imaginary part y. So here, both x and y are real numbers. All right, now in order to continue, we're going to need to find a relationship, not just for sine and cosine of real numbers, which we already know, not just sine and cosine of imaginary numbers, but we're going to need an identity or formula that allows us to understand what happens if we plug in complex numbers to sine and cosine. So let's go ahead and get to that right now. Now that we have the expectation to look for complex solutions to our equation, sine of x equals 2, let's get to work in trying to understand sine of z, where z is the complex number x plus iy, where x and y are the real and imaginary parts, respectively. Now there's a few ways that you can do this mathematically. The one that's most accessible right now is we're going to go ahead and apply Euler's formula and rewrite sine in terms of complex exponentials. Now the only change we're going to make is the input is x plus iy. So just replace x here everywhere with x plus iy. So let's make that our first step. Our identity gives us a factor of 1 over 2i. And we get e to the positive I, but now that's the input x plus iy. And the identity gives us a minus, a similar term, but with a e to the negative I times the input. So e to the negative I times x plus iy. Next bit of work is we're going to distribute the factors of I and negative I through the parentheses, and due to the addition in those exponents, we can split that apart as a product of exponentials using basic exponent rules. So let's do that. All right, if I distribute in the first exponential, I'll get e to the ix. And just be careful with your signs when you distribute I. We're going to have I times I, y, so I squared y. I squared is -1, so we'll be able to rewrite this as e to the negative y. We're going to do the same thing for the second complex exponential. Distribute the negative I, you'll get e to the negative ix. And now just be careful with your signs. Negative I times iy, you'll get negative I squared. That comes out to +1, since I squared equals -1. So your last factor here, you can write that as e to the positive y. All right, next, we're going to make use of Euler's formula and replace e to the ix and e to the negative ix in terms of sine and cosine. The only one that's not here on the board, e to the negative ix, just replace in between the plus to a minus, and it's pretty much the same identity. So let's again go ahead and apply Euler's formula twice. We have 1 over 2i. And now applying Euler's formula, we get cosine of x plus I sine of x, and that's times e to the negative y. We have minus, and then apply the related Euler's formula, changing the plus between to a minus. So minus, and then in parentheses, cosine of x minus I sine of x. And that's multiplying e to the y. From here, we can go ahead and distribute through the parentheses. And if we do that, we'll get e to the negative y times cosine of x. Looks like we have a factor of I, and then e to the negative y times sine of x. Again, be careful with your negatives here. Looks like we'll get a negative cosine of x e to the y. So I'll write that as minus e to the y cosine of x. And now distribute your negative. Those two negatives will change to a positive. And we'll write that as plus I e to the y. And that's multiplying sine of x. All right, that is a fair amount of work, all basic algebra here. We're going to notice in the brackets, we have two types of terms, those with cosine of x, the first and third terms, and we have sine of x terms, the second and fourth terms. Let's go ahead and factor out cosine of x, and then factor out sine of x. We're going to keep our 1 over 2i factor out front. If we factor out cosine of x, looks like we should have e to the negative y minus e to the y. All right, and that is multiplying cosine of x, since we factored that out. For your sine of x terms, your second and fourth terms, you can actually do a little bit better than just factoring out sine of x. You can actually factor out an additional factor of I as well. So let's do that. And it looks like you'll have in parentheses e to the negative y plus e to the y. And that is multiplying sine of x. And now we're going to notice the parts in parentheses look very similar to the definitions of the hyperbolic trig functions. The main difference, here the variable is y, but they're stated here with x, so just chain all your x's to y's. The other difference is we're missing these factors of a half. So you can take your factor of a half from the right side, flip it to the other side as a factor of 2. This one is close to the sine identity for hyperbolic sine, but we have our exponentials in the wrong order. So you can factor out a negative here. and then multiply the 1/2 over to give you a factor of 2, and you'll be able to rewrite this as -2 times hyperbolic sine of y. And a little bit less work, a little bit easier to see, this is practically the same thing as the right-hand side here for hyperbolic cosine, just missing that factor of 1/2. So multiply it to the other side to give you 2. This part in parentheses, we can write that as 2 times hyperbolic cosine of y. The last bit of work that we're going to go through is now we're going to distribute that factor of 1 over 2i to each term. And notice here you have a factor of 2i. Distribute to the second term in brackets. That'll cancel out completely. The first term in the brackets, you have a 1/2 times 2. That'll cancel out to 1, but you'll be left with -1 over I. And you actually can simplify that. Probably the easiest way is to take that, multiply and divide by I. And if you just multiply here, your denominators will give you I squared, which is -1. Negative times a negative cancels, leaving you with just I. So if you go ahead and distribute your 1 over 2i, your first term here, be left with a factor of I times cosine of x times hyperbolic sine of y. And distribute your factor of 1 over 2i here to the second term in the brackets. 2 times I cancels out completely with 1 over 2i, leaving you with sine of x times hyperbolic cosine of y. And that's it. We now have a way to understand sine for complex input values of the form x plus iy, and we can understand that now in terms of a combination of trig functions and hyperbolic trig functions. Now, the only change I'll make to this, we usually write a complex number with the imaginary part second and the real part first. So let's just switch the order, and we get our identity that we're after for sine of z, where z is the complex number, x plus iy. Our identity that we just proved or derived, we have that as sine of x times hyperbolic cosine of y. That's your real part for that identity. And we just add to that this part, the imaginary part, plus I times cosine of x times hyperbolic sine of y. And that is pretty much most of the work for what we need to be able to solve this equation. Sine of x equals 2, but now we're writing that as sine of z equals 2, since we have the expectation of looking for complex solutions. The only thing we need to go through now is just setting all this stuff equal to 2 and solving for x and y. Let's go ahead and make use of the identity that we just derived. We're going to replace sine of z with the identity here in terms of its real imaginary parts. And we're going to solve for x and y, the real imaginary parts, from here. All right, now we have on the left side a complex number. We have our real part and imaginary part. But on the right side, we have just 2, a real number. Let me rewrite the right-hand side as 2 plus 0i. And how we're going to proceed is we're going to equate the real parts, basically the parts without I. This part is going to equal 2, and it'll give us one equation. After that, we'll equate the imaginary parts to get our second equation. Let's go ahead and write them down. Equating the real parts, we'll get sine of x times hyperbolic cosine of y That equals the real part on the right side, 2. And now equating the imaginary parts, we get cosine of x times hyperbolic sine of y. That has to equal the imaginary part on the right side, which is 0. All right, and what we have now is a system of 2 equations for 2 unknowns, and we can solve that. Now we're going to start with the second equation. Since it's factored and equal to 0, we're going to get 2 possibilities or conditions. The first is that cosine of x equals 0. Or the other possibility is hyperbolic sine of y equals 0. All right, and we need to consider each of these individually. Let's start with the second condition. You might not be as familiar with your hyperbolic trig functions as you are with regular trig functions, but this is actually very easy to solve. Let's just go ahead and notice, if you were to plug in x as 0 here, you'll get e to the 0, 1, minus e to the 0, 1. 1 minus 1 is 0. So it looks like your solution here for y is 0. Now, to see if we actually want to consider this, let's go back to the first equation. And if y is 0, we're going to get hyperbolic cosine of 0. And if you check, plug in 0 here, hyperbolic cosine of 0, e to the 0, 1, plus another e to the 0, 1, 2 times a half. Hyperbolic cosine of 0 equals 1. This equation is going to reduce to now sine of x equals 2, which was our starting place for this problem. And we already know there's no solutions there when x is a real number. So we can forget about this and that whole second possibility or condition. Which means the only way we're going to get complex solutions is by considering this possibility, cosine of x equals 0. So let's go to some basic trig. Let's go ahead and visualize this. And on the basic unit circle, there's going to be 2 angles or points that correspond to cosine of the angle equaling 0. They're right up here at the top, corresponding to pi over 2. And you have another angle down here corresponding to 3 pi over 2. All right, now these are just your basic angles from 0 to 2 pi. Of course, each of these angles, you can go a full rotation or a multiple of 2 pi radians to get other solutions. All right, now we're going to, again, go into more detail. Here, these are where the cosine values are 0. Let's go back to your equation up here. What happens when cosine is 0? In other words, let's take a look at the values for sine. Sine of pi over 2, we know that's positive 1. And sine of 3 pi over 2 is negative 1. All right. How does this help us here? Well, if cosine of x is 0, going back to your equation, sine of x would be one of these 2 values, either 1 or negative 1. And if you take a look at your equation here, we have positive 2 on that right side, not negative 2. So we're going to forget about this possibility, forget about all these angles. And what we get here as your solution for the angle, in this case, x, we're going to say x is pi over 2 plus a multiple of 2 pi. And we'll write that as x is now pi over 2 plus 2 pi n, where n is an integer. So typically here n Might be written as taking on value 0, plus or minus 1, plus or minus 2, so on and so on. All right, and that right there, the fact that you have many, technically infinite, different values for the real part x, that's going to lead to our equation, sine of z equaling to having an infinite number of solutions. All right, now that's part of the solution here. We have now the real part, in other words, the value for x. We just need to get now the value for y, the imaginary part. Now, we're pretty much done. We're just going to make use of the fact that sine of any of these angles, in other words, sine of pi over 2, or any multiple of 2 pi, which just brings you back there, equals 1. This equation, your sine value becomes 1. So in this case, sine of x times hyperbolic cosine of y equaling 2. The sine of x part just equals 1. And we're left with hyperbolic cosine of y equals 2. And hyperbolic cosine of y, that does have an inverse function. So here we just solve for y by taking the inverse function, inverse hyperbolic cosine of each side, and we get it. We have our real part, the values for x. We have our imaginary part, and we're basically done. So let's just go ahead and write it. Again, we know from the beginning there are no real solutions to sine of x equals 2, which is why we switched it to sine of z. Z emphasizes we're thinking of complex values. So if our equation here is sine of z equals 2, we just found our solutions. Z was interpreted as the complex number x plus iy. And let's just go ahead and plug in. We have x here as pi over 2 plus 2 pi n. And don't miss your imaginary unit. We have plus I times y, where y is inverse hyperbolic cosine of 2. So I'll write this as plus I inverse hyperbolic cosine of 2. And we get it. And that completes our solution for sine of x equals 2. We had to go into complex numbers to find all the solutions here. And technically, again, just to state it, that value for n being any integer, 0, positive or negative 1, positive or negative 2, so on and so on, you get an infinite number of solutions to sine of x equals 2. You get an infinite number of complex solutions in that case. Hope you enjoyed the video. This was the very first video I did by request. So if you have other topics you'd like me to cover, leave a comment below and let me know. Hope you enjoyed the video. If you did, support the channel, like and subscribe.